forget, because sometimes I do forget. All right, it is exactly 3 o'clock, so let me get started here. The first thing I want to do is to get a quick survey. If you don't want to participate, that's fine. So the question is, if we get rid of CISP 300 and CISP 360, and then everybody's going to start at CISP 400, do you think that's going to fly? Okay, I see a lot of.
You can definitely get rid of 300.
Can get rid of 300, but not 360. Maybe. Yeah. So let me ask you another question, a follow-up question. Do you find a lot of overlap between CISP 360 and CISP 400? Some overlap, right? So if we get rid of CISP 360 and then the professor teaching 400, keep that in mind, would that still work?
I think you can teach 60 within 400, if that's what you're saying, you kind of
Yeah.
teach that as you go.
Yep.
It could be one class.
Okay.
I think it's really dependent on the students because like 300 and 301 is necessary if you have no groundwork in CS taking classes. Because I know when I was taking it, even like some people were still struggling, but still wanted to pursue CS.
Okay.
And I think it's important to have a class where you can start from nothing.
I
If you
see.
jump to 360, then you're already pretty getting into like the
Okay.
CS.
Let me explain a dilemma that I have. This is something that I have to deal with. It's not your problem. But what I'm getting the problem is, okay, so what you're seeing here is the TMC, or the transfer model curriculum. And this one dictates what makes an AST an AST. An AST is an Associate of Science transferable. So ideally speaking, we want the computer science degree to be an AST, because this one is recognized by CSUs and UCs. So that makes it easier for us to articulate with all the CSUs and all the UCs, with the exception of UC Berkeley, because they always want to do some things, on their own and different from everybody else. So in order to do this, the problem that I have is when they specify computer science, the TMC of the computer science program. Okay, let me download this and replace it. And take a look. All right. So the problem is, okay, it shows on the other screen, which I can now put it back here. This is what they're proposing. They want the entire degree to be only of 60 units and no more. So having all the GE classes and computer science, all the major classes added together, I cannot exceed 60 units. And right now, there is no way to contain all the units within 60 or less. And that's why we do not have an AST of computer science. We have an Associate of Science in computer science, but not an Associate of Science transferable, which is still okay because you can go through ASSIST and find out how we at ARC articulate with all of the other universities. So it still works. But it's not working in a very ideal situation, because ideally speaking, we want to transition to making an AST. And this is what the 4-year universities are proposing that our transfer degree should consist of. And you can see how they start off with Comp 122. Comp 122 is what we see as CISP 400. So CISP 300 and CISP 360 is not in the TMC. They did not account for the units for those two classes. So that's 7 extra units that I somehow had to find a place to squeeze them in. Do you see kind of what the problem is? So, and that's why I asked that question of, what if we get rid of CISP 300 and 360, and then I think that the consensus is it will make it very, very difficult for people with no prior exposure to computer science to get into computer science. Would you guys agree that's kind of the consensus? Yep.
If you still keep those classes, it just wouldn't count towards it
Yeah, but that becomes a problem too, because if it is not in the program, so let's just say that we do not include it in the program, then people cannot receive financial aid for those two classes. So there's that, issue also. And then also, if there are no other ways to get into CISP 400, and we only list CISP 360 as the prerequisite of CISP 400, then technically I cannot make the program not count CISP 360. So math doesn't have that problem because you can start right off with Math 400, because in the Math 400 prerequisite, it also says there's another way to get in, which is looking at the high school score of various subjects. That's how they can decide whether you can just start right off with Math 400, or or should you take Math 372, 373, or 375 these days. But we don't have anything equivalent to that. So we cannot, quote unquote, place people, based on their high school score. So anyway, I just want to show you, what kind of stuff I'm dealing with, and I want to collect your feedback of, what if we get rid of 300 and 360. Yep.
Can you do something weird, like make two different programs? So you have one degree that you could call it, computer science programming, and then another degree like computer science for transfer. And you have the computer science for transfer start at 400, but the computer science programming start.
Yes, we can do something like that, but it still does not address the issue of, what would be the prerequisite of CISP 400. So I have a plan. I have a plan of making a pre-computer science certificate that includes CISP 300 and 360, and also most of the classes that I think people should be taking within the first 2 semesters or the first year. So when people come here, the counselors would tell the students, okay, if you have no prior exposure to computer programming whatsoever, this is where you should start. You should get a pre-computer science certificate. It's not even a degree, it's a certificate. But it's going to overlap almost 100% with the computer science degree. So after people complete that first year, they will get a pre-computer science certificate. But they will also meet the requirement to get into CISP 400. So the idea is I would make a new class called CISP 409. It's a half unit class, or as few unit count as possible, and it's just basically one test to see whether people are ready to get into CISP 400. Do you see what I mean? So it's going to test people on just basic logic stuff, basic programming stuff, basic C++ type of topics. So anyone who passed CISP 360 should have no problem passing that test. And I will make that a co-requisite of CISP 400. So it's a little bit complicated like that, but what this means is people who are starting out with the pre-computer science certificate, they can get financial aid for all of those classes. And all of those classes would also, except for CISP 300, 360, would also count to the AST. And then now the AST does not need to include CISP 300 or 360. It's a little convoluted. The uncertainty is whether the curriculum committee, people who look at these things, whether they would say, but Tech, you're just coercing an exam into a class, and that's like trying to bypass the whole system, and they would say, nope, you cannot do that. So that becomes the only factor that I need to kind of ask people and see whether that will work or not. So, but thank you for your feedback, because that's actually really helpful for me to kind of figure out, try to figure out how to solve that problem. All right, so let me go find a instance of Canvas, which is here. And then we'll continue the topic on counting. This is something that we started last time. And I think we ended with the birthday problem, right? We calculated with a spreadsheet that with a class of, I think, 44 people, the percentage of the chances that two or more people in the class with the same birth date is 92% something. I think it was 92%. And that was not expected, okay? Or most people would not expect it. Because if you think about it, there are 365 days in the year, and 44 is about, what, 1/9 of that, right? A little more than a ninth. So you will not expect the chances of having two people having the same birth date to be 90-something%. In other words, if you have a class of 50, it goes up even higher. So that's what we did last time. And what we'll do today is to continue our discussion of general counting without replacement. Okay. Let me get back to this one. I believe we have talked about general counting when the outcome of each trial has exactly the same outcome set. So examples, okay, I'll give you some examples. Throwing a dice, okay, if you have a 6-faced dice, you throw it the first time, the possibilities are from 1 to 6, okay, fine. So your outcome set is going to be one in a set 1, 2, 3, 4, 5, 6, okay. You throw the same dice again, guess what? You get the same outcome set. The possibilities are exactly the same, 1, 2, 3, 4, 5, 6. You throw it 20 times, it is still 1, 2, 3, 4, 5, 6. In other words, one trial does not affect what choices are available for the later trials. Is that okay? So in those cases, your T0 all the way up to T subscript m-1, each one representing the outcome of a single trial, they're all the same, okay? I just use the index here to say, oh, this is the outcome set of the first trial, second trial, third trial, and so on. But in the end, they're all the same. And I forgot to turn on my screen share. So let me get this going. All right. And where's my OBS? There we go. There we go. All right. And as a result, T0, T1, T2, all the way up to T subscript m-1, they're all the same. So when you need to figure out, at the end of the entire experiment, the number of possible outcomes for the entire experiment, it's just, if you want to find out the number of possible outcomes, it's going to be the product of the cardinality of each outcome set of each trial. But if they're all the same, in other words, if T0, T1, all the way up to T subscript m-1, if they're all the same, we'll just call it T. Then we have one single cardinality to deal with, which is just the cardinality of T. So with a 6-faced dice, this is just 6. If you're flipping a coin, it is 2, and so on. So we just call it N. So that means the cardinality of the entire experiment of M trials, or I should say the cardinality of the omega, or the outcome set of the entire experiment of M trials, is going to simplify to N to the power of M. So that was, I think my phone thinks I'm talking to it, but I'm actually not. All right, so let me see if I can turn it to, with airplane mode, turn that off? I think so. No? All right, so this is the cardinality. And in the example that we talked about the class with birth date issues, the question, so it would be 365 to the power of the number of people in class. That's the total number of ways to arrange birth dates within the entire class when there's no restriction. Does that make sense? Because each person, you can choose one of the 365 days in the year. So can you, so can you, so can you, and so can you, and so on. So that means, of each day that is possible to you, you have 365 choices. And then for each day that you have chosen and for each day that you have chosen, you also have 365 choices, and so on. So from that perspective, that's why we have 365 as N, and then M would be the number of people in class. Is that okay? Are you guys kind of remembering what we talked about last Wednesday? All right, excellent. So now we get into the issue of what if it is without replacement? So a common restriction to trials in one experiment is whatever is chosen earlier cannot be a choice in later trials of the same experiment. Let us assume that we start with a set T, where n equals to the cardinality of T as the set of outcomes of the first trial of an experiment with m trials. Okay, so this is really abstract, lots of words. The easiest way to look at this is you have a bag of marbles, okay? So let's just say that we number the marbles from 1 to 69, okay, to match the lotto game. So that would be a bag of marbles. But every time you choose a marble out of the bag, you don't put it back in the bag. So that means you have 69 choices to pick the first marble, right? Because that's when the bag has all 69 marbles, right? But once you have chosen the first marble, you set it aside, and now you want to pick again. But the second trial only has 69 minus 1 marbles, or 68 marbles, because the first one is not available to you anymore. Is that okay? Does that make sense? All right? So if E0 is as an element of T is the actual outcome of trial 0. So let me just kind of focus on this sentence alone. So in this case, E0 is representing what we actually chose for the first trial. Okay? So that marble is now out of the bag. It is not in the bag anymore. Then E0 is no longer available for trial 1. Trial 1, therefore, has an outcome set of T minus and a singleton set that has only E0 in it. And there are now, the cardinality is n minus 1, because we know the cardinality of T is n, and we know E0 is an element of T to begin with. So this subtraction here, or this difference of two sets, is guaranteed to have n minus 1 choices in trial 1. So let me just kind of pause here and make sure that we all understand this particular paragraph or the meaning of that paragraph. Is that okay? It simply means that every time you perform a trial, you take a choice away from the further trials within the experiment. Are we good? All right. So using E of I to represent the actual outcome of trial I, it is easy to see for trial I, the outcome set is going to be T minus. Now this big U notation here is basically a loop. It's a loop where the index starts with J. The index J starts with a value of 0, and it ends with a value of I minus 1. In other words, we are basically just saying T minus in a singleton set E0 unioned with E, a set of with only E of 1, E of 2, and so on, all the way up to E of I minus 1. So we have to remove all the chosen marbles from the bag in order to figure out for trial I, what choices do we have left. Is that okay? Does everybody understand the notation, the big U notation, which is kind of like a sigma notation? It's basically going through a loop, except instead of adding, we are now performing the union operation for each set that is generated for each iteration of the loop. Are we doing okay so far with this part here, this little expression? All right. So as a result of that, if you want to look at the cardinality of the outcome set for trial I, it would be n minus I. Now, why is it n minus I? Well, we know each one of these used to be in T originally. And so when we have, okay, so if you just look at these two, okay, if you just say J is an index that starts with 0 and it ends with I minus 1, how many iterations are we talking about? It will be I iterations, not I minus 1 iterations, because we started with 0. Okay, so that's the whole thing. So there are I elements that we are removing from T. T had n elements to begin with, and that's why the cardinality of this entire thing is just n minus I, because we started off with n elements. For each iteration, for each trial, we remove one item from the bag, and one after I trials already, then we have n minus I choices left. Is that okay? Okay, all right. So now we want to look at, from the counting perspective, an experiment with m trials has the following possible outcomes. So we are counting the number of outcomes. We are not looking at what is each outcome. We're just counting how many outcomes we're talking about. So we have this big pi notation. The big pi notation is the same thing as a sigma notation, except we're not adding, we're multiplying. So for each iteration, depending on what the value of I is, we're generating a value, and then we are multiplying all of those values, over the range of I equal to 0, all the way up to I equals to m minus 1. Is that okay? As far as the notation is concerned. Okay? And because if I'm talking about trial I, the number of outcomes for that outcome set, the cardinality of the outcome set for trial I is n minus I. We talked about this a little bit earlier. When I equals to 0, we're looking at the outcome set of trial 0. Trial 0 being the very first trial has all the items in T available to it, and therefore n minus 0 is just n. So the first trial has n available choices. What if I equals to 1? And when I equals to 1, which means we are looking at the second trial, it has one fewer elements, because the first trial took away one choices out of everything in T. So the second trial, which is marked by I being 1, is going to have n minus 1. That would be the number of possibilities for trial 1, which is the second trial, and so on. Are we still doing okay so far? Okay. So the way we work this out is we want to express things using operators that we're familiar with. In this case, it would be factorial. So what we do, or what I do here, is I multiply with a term that looks really silly, which is two big pi terms, each one being a product of a bunch of stuff, and we have they're identical. In other words, when you look at this particular term here, it just boils down to 1 exactly. So it shouldn't hurt anything. So from the first line to the second line, you can see that, hey, what just happened here? Because this pi notation somehow got absorbed into the numerator of the fraction. How did that happen? What is the math behind it? So the way we think about this is we look at the denominator. Okay, the denominator has not changed. Okay, not at all. Okay, it has remained exactly the same. So we're only looking at the numerator and the thing that was outside the numerator. So when you look at the pi notation or the sigma notation or the union notation and stuff like that, what is the range of the index is really important. And that's what we're going to focus on. If you look at the outer pi notation, I'm going to use my mouse pointer to point to it. If you look at this one, you can see how I is ranging from 0 to m minus 1. When you look at the numerator, you can see how that I is ranging from m to n minus 1. So what do you notice about those two ranges? One is here, and the other one is contiguous to it. Let me say that one more time. The two ranges are two partitions of the same bigger range, except I just chose a point to break it apart. Because the first pi notation goes from 0 to m minus 1, right? The second pi notation picks it up at m, and it goes all the way to n minus 1. So that means I can now combine these two pi notations so that the index would simply go from 0 to n minus 1, because the two ranges, one from 0 to m minus 1, the other one from m to n minus 1, they are really just two partitions of the same range, and those two ranges are contiguous, which means the end of one is right against the beginning of the next one. Is that okay? All right. So now we look at this notation and go like, what are you going to do now? Well, the first thing we do is, how do we go from the second line to the third line? That's kind of the question. So what we do is we flip it around, okay? What do you mean by flip it around? So we look at the range of values. So we'll focus on just the numerator. If you look at the numerator, what is the first actual value that we are multiplying? Well, when I equals to 0, n minus 0 is just n itself, right? What about the next one? Well, it's n minus 1. What about the next one? N minus 2. And then the last question is, what about the very last one? The very last one is when I equals to n minus 1. So now the question is, what is n minus in parentheses n minus 1 close parentheses? That's just 1. So that means if you look at the terms produced by the numerator, the pi notation of the numerator, it really is just counting backwards. n minus 1, n minus 2, n minus 3, all the way down to 1. Is that okay? And I'm trying to make a product out of those individual terms. Is that okay? So why don't I just say this? It seems a lot easier to say that, don't you think? I'm just saying, okay, let's just say that I goes from 1 to n, and then each term that I am multiplying to the entire thing is I. That sounds a whole lot easier. Because now it is just saying, oh, okay, so we actually end up with exactly the same terms in the product. It's just spelled out differently. Instead of starting with n and then times n minus 1 times n minus 2 all the way down to 1, now I'm starting with 1 and then times 2 times 3 all the way up to n. Is that okay? Does everybody see how the pi notation from the second line to the third line is really coming up with the same product, except the ordering of how the terms appear is reversed? All right. What about the numerator? So we look at the numerator here, and it's kind of the same deal. So what you do is look at the numerator, and you ask, how does the numerator go from here to here? So you substitute I with m first. So the first term is going to be n minus m, and there will be n minus, in parentheses, m plus 1, plus 2, all the way up to n minus, in parentheses, n minus 1, which turns out to be 1. Is that okay? We're still counting backwards, okay? We're still decrementing for each iteration, except the starting point is different compared to the numerator. So what I did from between the second line and the third line is I just go like, how about we put the last term as the first one? So we start with a 1, and then we put the first term to the last, and that would be n minus m. Is that okay? Can everybody see how the denominator is really the same value, except this pi notation is counting down to 1. This one is counting up to n minus 1 from 1. Is that okay? Why would I do something like that? I mean, that seems like just a whole lot of work for no particular reason. Well, that's because this is how we define n factorial. This is what n minus m factorial looks like. So now I can transition this to n factorial divided by n minus m factorial. And the notation is basically a p using m as a subscript and n as a superscript. That is the way you express the number of permutations when you start off with n choices and you choose m things out of it. Are we okay so far with the notations? I know this stuff is kind of dry and Kind of boring, but are we good? All right. If you are to use a spreadsheet, because I know some people like myself like to do all the calculations in the spreadsheet, the P is known as permut. P-E-R-M-U-T, which is permutation. All right. But now we are looking at permutations. So two permutations can have exactly the same things in it, but the ordering is different. In other words, a permutation is a tuple, where ordering is important. But there are certain cases where ordering is not important, like in the game, in the lotto ticket, how you choose those 5 numbers is not important. Or in a drawing of those 5 numbers, the sequencing of those 5 numbers does not matter. So how do we take care of that problem? So that's what section 5 is about. So in some cases, ordering of trials in an experiment is not important. For example, in the case of lottery, choosing 1, 2, 3, 4, 5 is the same thing as choosing 5, 4, 3, 2, 1. Or I should say, the drawing of the numbers 1, 2, 3, 4, 5 and the drawing of the numbers 5, 4, 3, 2, 1 would be considered equivalent because, when you get a number in the sequence does not matter. In this case, the set 1, 2, 3, 4, 5, note the use of the set notation, is known as a combination. So a combination is different from a permutation, where permutations are ordering dependent, and a combination does not care about the ordering. Okay, is that term understood? What I mean by whether ordering is important or not. So far we have seen 2 examples where in one example the quote-unquote ordering is important, and in the other example the ordering is not important. So we'll first talk about the example where the ordering is not important. That's lotto. Okay, so when you watch a lotto drawing, there's a big gigantic basket rolling, and then they pick up these balls with a number on it, right? So the ordering of which ball is picked up in which position, that's not important. All I need to know is that number one of the drawn numbers? That's all I care. Membership is the only thing I care. I don't really care the positioning of that thing. So that's when we use combination. When did we use permutation? We used permutation in the birthday problem. Why? Because let's just say that we are talking about the first 3 students in this row. Okay, so whether you have date 1 and then you have date 2 and you have date 3, versus you have date 3, you have date 2 and you have date 1, that's different. They're considered 2 distinct outcomes of the experiment. So that's why quote-unquote ordering is important, even though in this case there's no actual ordering per se. It's just whether you have the first date, you have the second date, you have the third date, versus the other way around. Does it make a difference? And the answer is yes. They make a difference. They should be counted as 2 different outcomes. And as a result, each one is called a permutation because ordering is important. Are we okay so far with that concept? When permutation is applicable? Yep. Say that one more time.
It matters. The order matters because you removed an element out of the total number of choices.
Almost. It is important because 1, 2, 3 and 3, 2, 1 are considered 2 distinct outcomes. They're counted as 2 different outcomes as opposed to looking at 1, 2, 3 and 3, 2, 1 as 1 single outcome. Okay, let me give you, maybe this will help. Lotto drawing video. Let me see if they used to have these videos. Oh, okay, there we go. I'm not sure whether I would have a copyright infringement like last time because of the beer commercial. So we'll see. There we go. So they pick 44 first, 62. Okay, I think this is enough to make a point. Okay. Oh, okay, I just played.
Room doctor, Greg Moore.
Hmm?
MD. I was reading that.
Say again?
I was just reading what it was saying on the commercial.
Oh, commercial. Okay, I just need to find the right point. Okay, now I'm going to stop. So they ended up picking 5 numbers, as the winning numbers, and then plus the extra number, which is the Powerball number, right? So we're going to ignore the Powerball number. We'll focus on the 5 winning numbers. The idea is, whether we chose, whether we pick up 62 first, or whether we pick up 44 first, doesn't make a difference. Because all we want to do is to say, okay, let's look at the 5 numbers on your ticket. Does it have 44? Yes or no? Does it have 62? Yes or no? So there's no inherent importance to the ordering when they pick up these 2 numbers. Does that make sense? As opposed to the birthday problem, where does person A have this birth date and does person B have another birth date? Exchanging those 2 birthdays for those people would mean 2 different possible outcomes. Is that okay? Does that, okay. All right. Another way to kind of look at this is usually when we're looking at a combination, we only care about membership. In other words, we only care about, is that thing one of the things that you chose? Okay? But I don't really care when you choose it. I just want to know whether it is something that you have chosen, but I don't care whether it's the first thing that you picked up, that you chose out of the outcome set, or the second, or the third. It doesn't matter. It's just that, did you choose that? Okay? All right. So in this case, 1, 2, 3, 4, 5 is known as a combination because it is a set, as opposed to 1, 2, 3, 4, 5 in parentheses, which is a tuple, or it is a permutation. So there are many other permutations from the same combination. Now this sentence is kind of important. Okay, let me just highlight it first, and then we'll talk about it. All right, so this is the sentence that I want you guys to kind of think about and see if you have any questions. This is basically saying, if I give you one single combination, there are potentially multiple permutations associated with it. So in this case, in this particular example, we have a combination of 1, 2, 3, 4, 5, which means how 1, 2, 3, 4, 5 is arranged in a set doesn't matter. So the question is, out of these 5 members, okay, how many ways do I have to arrange them so that the ordering is important? So we have 1, 2, 3, 4, 5. We have 1, 2, 3, 5, 4. We have 1, 2, 4, 5, 3. 1, 2, 4, 3, 5, and so on and so forth. So what would be the total number of permutations corresponding to the same combination in this specific case? You guys know how to get to that answer already. It's just a matter of remembering what we are dealing with here. Does anyone want to give it a try? All right, so we have 1, 2, 3, 4, 5. So imagine 1, 2, 3, 4, 5 as choices in a bag. Okay, so I have a bag here. It has 1, 2, 3, 4, 5 in it. This time, ordering is important. So I reach into the bag, and how many choices do I have, to pick out the first item? 5 items, 5 choices, right? So 1 can be the first one, 2 can be the first one, 3 can be the first one, 4 can be the first one, and then 5 itself can also be the first one, right? Let's just say that I chose 2 first, okay? So I picked it out and go like, oh, it's a 2. How many choices do I have for the second item that I choose out of the bag? 4 choices. Exactly which 4 choices? 1, 3, 4, 5, because 2 is already out, right? Let's say I picked 5, as my second choice. What about the third one? How many choices do I have? 3 choices. What are my choices? 1, 3, and 4. Because I think 2 and 5 are out, right? So that's how we can, but the ordering is important. So my question is, how many ways can I arrange 1, 2, 3, 4, 5, where ordering becomes important? Okay, so the way, yeah, go ahead. 120, because it is 5 times 4 times 3 times 1 times 2 times 1. So it is 120. So what do we do about the 120? Well, we look at the permutation thing. And if you need, okay, so what is this? The C notation is choosing M out of N where ordering is not important. So we are counting the number of combinations. So this is the other notation of N choose M, is to have a parenthesis where you say N as the top item and M as the bottom item. It may not be easy to write, okay, using a text editor, but I do have LaTeX, which makes it easy to format. So the first line is not too important other than it tells you 2 ways of expressing the same thing. The second line is important because what it's trying to say is you can derive the number of combinations by first computing the number of permutations. Because when you compute the number of permutations, you're just overcounting, okay? You're counting duplicate permutations, because ordering is important when you really don't care about the ordering. So what you can do in that case is to say, I'll get to the number of permutations first. I know this number is inflated. And then I try to factor out, how inflated is this number? Well, how inflated that number is, well, if I pick out m items, how many duplicates do we have? Well, there are m factorial duplicates, because for m items, there are m factorial ways to arrange their ordering. Is that okay? So once we divide m factorial from the number of permutations of choosing m items out of n, then we end up with this final form, which is n factorial divided by m factorial times, in the denominator, n minus m, the entire thing factorial. Whew. Okay, so are we okay so far with the math stuff? So let's just say that you're reading all this stuff here, and you're almost falling asleep because there's just a dry stuff, a lot of numbers, a lot of symbolic manipulation. What are you going to do? How do you make it easier to absorb the material? Coffee is not an option. Coffee is just time on loan. You still have to, pay that later, pay for it. So what would be a good way for you to kind of start to understand this stuff, but in a more kind of hands-on way? Yep. Excel, or you can just work it out. Okay. One way to work it out is, okay, I can show you. So let me show you. I'm looking for my text editor. Okay, it's down here, right there. All right, so I can show you what I mean by that. Okay, let me get rid of this. So let's just say that we have 4 items. Okay, 1, 2, 3, A, B, C, D. Okay, A, B, C, D. I want to choose 2 items, and ordering is not important. Okay. In other words, I'm trying to figure out the number of ways to choose 2 items out of 4, and ordering is not important. Are we good so far? The math that we have seen is to say, well, one way to do it is to start with the number of permutations. In other words, I'll pick 2 things out of 4, and then we'll consider ordering be important first. Does that make sense? So now we say, I can choose A as the first item, and then I can choose B as the second. I can choose A as the first, C as the second. I can choose A as the first, D as the second. Then I can choose B as the first, A as the second, B as the first, C as the second, B as the first, D as the second. I mean, you guys can see where this is going. C, A, C, B, C, D, and then we have D, A, D, B, D, B, and then D, C. So there are exactly 12 ways to get 2 items out of 4, and we count the ordering as important. Because you can see how AB is counted as 1 item, and then BA is counted as a second item. Is that okay? So if I just say, well, hold on a second here, okay, I don't care about the ordering. So if I don't care about ordering, how do you figure out the number of ways to choose 2 out of 4? Well, then you look at these 2, okay, I will attempt to, this is the set of AB, and so is this, right? So these 2 are the same. I overcounted 1, okay? 1 is an overcount. And then I look at AC. Oh, by the way, CA is also over here. I look at AD, and DA is also over here, and so on. So to me, the question is going to be, well, what is the ratio? Okay, in other words, if I look at one particular way to get 2 items, how many times does it appear here as permutations? And that turns out to be 2 factorial, which is just 2. So if you count, okay, so now, as a summary, if you are to look at the number of combinations and not the number of permutations, then we only have, let's see, AB, AC, AD, and then we have BC, and then we have BD, and then we have CD, and that's it. So there are 6 combinations, but there are 12 permutations. So this will give you an idea of, oh, okay, so if I look at 4 factorial, it is 24. Excuse me. 4 factorial is, yep, it is 24. But we have to divide it by 2 factorial to get to the number of permutations. 2 factorial is 2. 24 divided by 2 is 12. So I have 12 permutations. But if I need to figure out the number of combinations, I have 4 factorial as the numerator, and then the denominator is going to be 2 factorial times 2 factorial, which is 4. So it will be 24 divided by 4, which is 6, which is exactly why we have these 6 combinations here. So what I want to say is reduce the size of the problem and actually work it out by hand. So that will help you understand the concepts instead of just reading the notes, which is really abstract. Work out small examples. Is that okay? All right? Okay. So now we are done with counting. And we're getting into, I'm just looking at the time. So now we're getting into, well, what if I'm not interested in the number of permutations or the number of combinations? What if I want to know the actual combinations and the actual permutations? In other words, I want a list of ways to arrange something, or ways to get something out of a bag. I don't want to just count. I want to know the exact combinations or permutations. So what if that is my objective? So why would I want to generate something like that?
Like matching tool or something like that, or even
Mm-hmm.
like a pairing list or something.
Well, sometimes you can use it. Okay, have you guys played the Mastermind board game? No? Okay, I can see a lot of people do not know the Mastermind board game. Okay, so Mastermind board game. Okay, so this is the Mastermind board game. so you need, it's a two-player game. One person has the easy job and the other person does all the heavy lifting. Okay, so it is facing the guy who holds the secret code. So the other side is going to be the person who's going to do all the guessing. I believe there are variations of this game. The one that I'm familiar with has 6 different colors. So there are 6 colors to all the pegs. So the guy who's hiding this code is going to say, I'm going to come up with a, it's not a combination, because you can actually duplicate the same color. But the idea is I'm hiding behind here a code or a sequence of color pegs. Okay, is that okay? So I can say orange, yellow, red, and green. Okay. So the job of the other person is to quote unquote crack the code, is to find out what my secret is. And I can give the other person clues like, well, you got one that is at the right position and the right color, and one that is the right color but is at the wrong position. So I can give the other person a clue as to, okay, how would I score your current guess? Okay, so the game is about how many moves the other person, the guesser, needs to make in order to log down to, in order to zero in to my exact pattern that I'm hiding. That's the name. That's the game. So you can see how maintaining a list of possible arrangements is going to be helpful, because every single time the person is making a guess and I'm providing the feedback, I can help that person to eliminate a bunch of how the colors can be arranged. So the next guess, okay, is supposed to optimize the whole thing. In other words, the person is supposed to pick something that will help differentiate, okay, of all of these choices left, okay, which guess should I make to minimize the number of steps leading to the full resolution of the actual code that is being hidden. So that's just one of the many reasons why you might want to generate combinations or permutations. Password does not, even this is not a very exact example, because it's not a combination nor a permutation, because in this case you can repeat a color. So you can have red, 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 and red as the hidden pattern, but that would be very easy to guess. So we still doing okay so far with why in certain cases you might want to generate the actual set of combinations or permutations. Okay, I'll give you another example. From the perspective of the lotto game, don't you think it might be helpful to kind of be able to generate all the possible tickets? All right. All righty. Or, okay, so here's the other thing. So let's just say that we are now dealing with a society where if you tell someone, if 2 out of the 5 lucky numbers are matched, and you do not match the Powerball number, you're gonna make this much money. Just come down to 7-Eleven and we'll give you the cash, right? What if the population is going to a point where they don't understand the instruction? I don't know how to match 2 out of 5 of the numbers of my ticket. Then what the lotto game people would do is they will generate every single way to match 2 out of the 5 numbers and not matching the Powerball number. And then the person who just bought a ticket for $2 is now going down a long list. It's like, oh, I'm not matching this. Okay, so that would be another application of generating, in this case, combinations. Is that working out okay or not? Okay, I can give you another one. Okay, so let's just say that there are 6 destinations. Okay, so a family decides to go on vacation. There are 6 possible destinations, and then there are some rankings that are related to the destinations. So now you want to basically figure out, okay, there are 6 possible destinations, but the family can only go to 2 of those. Is that okay? And you want to optimize and go like, okay, but we want to figure out, which 2 are the best destinations. So how do you do that? Well, don't you think you have to come up with all the combinations, and then for each combination, you calculate the weight or the score, and then you pick out the best combination and go like, I think this year we should go here and here because, according to the scoring criteria, this combination of destinations is the best.
It's like the route this route optimizer work something similar. It's a bit different though, but
It's
you still give it a list of destinations, and then it's like this combination is the best.
right, but you have to be able to generate all the possible combinations first in order to make sure that you're not missing a particular combination when you're trying to figure out which combination is the best combination. So there are various reasons why we want to generate the permutations or the combinations depending on whether ordering is important. Does that make sense? Okay, because I want you guys to be convinced that there are applications where you want to be able to generate the actual combinations and permutations. Okay? All right. So now that we have that out of the way, we are going to start with the permutations. How do we generate the permutation outcome set of an entire experiment? And we are not, there are no replacements. So once you take an item out, we're not putting it back in. So the notation is really important, so we're going to go slow in order to read all the notations. In the cases where the outcome set of each trial T of I is independent to other trials, the outcome set omega of an experiment of M trial is just the Cartesian product of the outcome set T of I, where I is an element of 0 to M minus 1. So that's not the exciting part. However, with the concept of without replacement, the outcome set of an experiment gets a little more difficult to express. The cardinality of the outcome set is already discussed, and it is relatively easy to derive. So what we did before, using the P notation, is we get to the cardinality. That's the easy part because it's just factorial. But what this section is trying to do is to generate the actual permutations. So to do that, we're going to use T to represent the pool of choices originally presented to trial 0, or the first trial. Furthermore, I'm going to use this notation, omega I of T, to represent the outcome set of an experiment involving I trials, starting with T as the set of trial outcomes. Okay, so let me just kind of highlight the sentence and then see if you guys have any questions about this. So this time, omega is not just the name of a set, it is the name of a function. So omega I of T is going to give me a set. What is in a set? What are the members in this particular set? Each member is going to be a possible outcome where ordering is important. And we start with T as a set of outcomes, and we are going to choose I things out of T. Is that okay? For instance, if T is A, B, C, D, E, and I is 3, then I'm asking, if I have A, B, C, D, E in a bag, and I want to pick out 3 things out of the bag, how many different ways can I choose? Can I get 3 items out of 5 from a bag? And ordering is important, which means if I get A, B, C in that order, it will be considered different from C, B, A in that order. Is that okay? All right. So the first one is the base case. So the base case is, what about omega 0 of T? Okay, so we want to understand this notation first, okay? So we are given a bag of 5 items. Okay, T has A, B, C, D in it. It's a set. And we are saying we have no trials. Okay? So without any trial, what is the set of the outcome of the experiment? Most people would say, oh, shouldn't it be the empty set? The answer is nope, it is not an empty set. Instead, it is a set that has an empty tuple in it. What? Right? So what you do, what you want to imagine is this. Okay, so I can only do this on the whiteboard, but I will describe what I'm drawing on the whiteboard because I didn't start up Zerno. I actually did start up Zerno, didn't I? Okay, let me see if I have it already. Nope, I did not start up Zerno. So I'm going to draw on the whiteboard. So on one hand, you have a bag of items, okay, marbles or whatever. On the other side, you have a tube. Okay, so we'll just say this is a tube, which is supposed to contain things that you get out of the bag. Is that okay? Now, it's a tube where the diameter matches the ball or the marble, of the bag. So that means once you put an item in, they cannot shuffle and change position in the tube. Does it work? Okay. So the initial problem, which is what we have here, omega 0 of t is an empty set. That's basically saying, yep, this is the initial condition. I'm giving you a bag of a bunch of items. I'm giving you a tube so you can put those marbles into the tube. And then go like, okay, pick nothing out of the bag. You go like, and I ask you, what's in your tube? You go like, there's nothing in the tube because you did not ask me to. You asked me specifically not to take anything out of the bag. But it is still an outcome. The empty tube itself is an outcome. Your tuple is empty. Is that okay? This is a conceptual thing, okay? This is not a math thing. It is not a programming thing. It's a concept thing. You still have an outcome. Are we good so far? It is representing a base case because the definition is recursive. I need to stop at some point. So I can now say safely and say, if you ask me to choose nothing or take nothing out of a set to put it into the tube, I know what the answer is going to be. I'll give you an empty tube back and say, that's the only outcome because you asked me not to take anything out of the bag and put it into the tube. Is that okay? It sounds trivial, but it is very important because otherwise the recursive definition would not know when to stop. Is that okay? Are we conceptually accepting the fact that an empty tube is still considered as an outcome? Okay, all right. So now we can go for the recursive definition. So the recursive definition says, okay, this is the recursive definition. So let's take a look at the recursive definition here. Omega I of t. Okay, so once again, let's find out what omega I of t is trying to say. We have a bag of items, that's t, and we are told to take I things out of the bag and put those things into a tube in that order. So the first thing you get out of the tube would be the first item in the tube and so on. So my question is, how many different ways can we do it? Now we have already worked this out earlier in class. So the examples that we have worked out so far is this, okay? So this particular example is saying, what if t is A, B, C, D, and I is 2? Then the tube having A and B in it in this order is one possible outcome. The tube having A and C in it in this order is a second outcome, and so on. Is that okay? All right? So now when we get back to this notation here, then we ask, how do we get that? So we have a big union here, which means we are taking each. This is a loop, okay? So the loop is looping over each element of T. Is that okay? So this is not using an index I where it's numeric. This time we are basically iterating through each element of the set T. If your set has A, B, C, D, E in it, that means we have one iteration with A as E, and then we have another iteration with B as E, C as E, D as E, and unfortunately E as E. So we have 5 iterations in that case. Is that okay? Does everybody understand the notation of the big U where we're iterating through each element of T? All right? So once we have chosen which element of T is supposed to be E as a variable, this is the term from this open paren to this close paren here. That is the expression that we are going to union with all of the other terms from the other iterations of the same loop. All right? And what exactly is that term? Well, that term actually is not very complicated because we have E as the only element within a set. This is Cartesian product. And then we have the recursive call. The recursive call is basically saying, okay, let me think of the best way to describe this. I know exactly how to do it. So I got this bag here. Okay, so just to describe what I'm doing verbally, I got this bag here, and we'll just say that this bag has 7 items in it. Okay, so there's 7 things in it, but I want a tube filled to only 3 items. Is that okay? I got 7 marbles in the bag. I have a tube, and I want to find out all the different ways to choose 3 marbles out of the bag and fit it into the tube. Is that okay? So the way recursion works is to break down a larger problem into smaller problem and one additional step. And each smaller problem, guess what, has the same nature as the big problem to begin with. So the way I'm going to do this is I'm going to give it to a person and say, this is the original problem. You don't have to actually do anything. I'm just using it as a prop. And there are 7 items here. You get to choose 1 item and put it into a tube. So here's a tube. So you reach into the bag, you pull out 1 marble out of it, and you put it into the tube. But the problem that I gave you is not just that, because I want you to give me all the permutations. Then you go like, okay, I suppose I can get this item out of the bag as the first item, put it in the tube. But in an alternate universe, I can choose another thing, another marble, put it into the tube, and so on. But how do you figure out all the sub-problems? In other words, you don't want to do all the extra work. So what you do is you go like, okay, so I can figure out what my choices are. The marble that I can put into the tube will be one of the 7 original marbles, right? So after you have chosen the first marble, you want to figure out, okay, what about the other 2 marbles that are supposed to be in the tube? What are those configurations? You go like, I got something else to do. Why don't you do it? That's recursion. It's basically delegation. So what do you think he's going to describe the problem to you? He's going to say, well, here's a bag with only 6 items because you chose one already. It's already in the tube, right? So he will tell you, how many are you supposed to work with? 6 marbles in the bag, but how many more items, how many more marbles are we supposed to fit into the tube? Just 2, right? So you go like, okay, great, thanks. Now I have a job to do. So there you say, okay, fine. Of the 1 item that is already in the tube when you're given the tube, that one you cannot change. But you can say, well, guess what? I got 6 choices for the second marble. So you pick one thing out of the 6 marble. You pick one of the marbles out of the bag, 1 out of 6, right? Put it into the tube. Now the tube has 2 items in it, right? But then you go like, oh, but he told me that I'm supposed to figure out the number of ways to put marbles into the tube, and there are 2 that you're supposed to deal with. You go like, I don't have time for that. Why don't you do it, right? So what is your problem? The problem that is given to you is now the bag has how many things in it? 5 marbles, and the tube is already filled up to 2 already. So your job is to fill it with 1, right? So you go like, okay, fine, I'll pick 1 marble out of the 5, stick it into the tube, and then go like, okay, but you don't know that you're done, right? Because this is not the terminal condition. The terminal condition is when you're supposed to pick nothing out of the bag. You were told to pick 1 thing out of the bag, so you're not the terminating condition. You don't see the terminating condition. So what you do is like, it's your turn now. So what is the description of the problem that you need to solve? So from his perspective, how many marbles are left in the bag? There are 4 marbles, right? So the 4 marbles in the bag, the tube is already filled up to 3. So how many marbles are you supposed to take out of the bag and put it into the tube? 0. It's already done. So you look at the code there and go like, well, I'm not going to put any more thing into the bag, into the tube, right? And therefore the recursion ends. So after this entire sequence, we just figure out 1 way of taking 3 things out of the bag, right? So when you're done, because you got nothing to do, because you're not adding any more thing into the tube, so you go like, okay, I'm done with that problem. So what you need to do now is to say, well, of the marbles that my predecessor gave me, I now kind of retract that, take that marble out of the tube, and then look into the tube and go like, okay, what about the second marble that I pick up? Put it into the tube, and then give you this empty problem to solve. And so it's going to go between you 2 for a while. So when you have explored all the possible ways to put the 5 marbles as the last marble, then you give it back to him. So now you go like, okay, so now we have figured out all the ways to put the last one. So now you are free to choose the next marble available to you. And now you have a bag of 5 marbles again, but it's slightly different from last time. And then you get the same problem as last time. But it's not going to be exactly the same 5 marbles as last time because 1 has changed. So do you see how the recursion is working? So the recursion is in some way all about delegation. But each time you delegate to the next person, the nature of the problem is the same. But the size of the problem is a little bit smaller. Is that okay? And this is just the really cryptic way of saying the same thing that I said earlier, except using the symbols that we have talked about already. Is that okay? All right. So I don't have enough time because with 5 minutes I cannot give you a trace of doing this by hand. Okay. But what I can do is to set up that problem for next time. So what I want to do is to set up that problem for next time. And I don't want to do something like this because that's just going to be taking a long time. So I want to do something like this, T of 2 of a set that has 3 items in it, like that. Whoops, that's not T. Got the wrong term here. This is omega, Okay, so this is what I want to solve next time. Okay, on Wednesday, when we come back, I'm going to solve this one by hand. But I'm going to do it recursively, and I'm going to give you the trace of how this is done recursively by hand. But what I want you to do is to try to do this at home before we meet on Wednesday, just based on the definitions of the omega. Try to solve this one, okay, omega of 2, And then the set, the first set is A, B, and C, just 3 items in it. We already know what it's supposed to have, okay? The outcome set is supposed to be a set with AB, BA, AC, CA, BC, CB. Those are supposed to be 6 tuples in the outcome set. So we kind of know what the end result is supposed to be, but we want to be able to apply the recursive definition. And because it's relatively small, so I want you guys to be able to do this by hand. And then on Wednesday, I will go over that in class so that you guys can ask questions as I go over the steps. But I think it will be very helpful if you at least try to do it first, because then you will know what questions to ask as I go through that process. Is that okay? All right. So just to give you an outlook of what we are going to talk about next. So we have one for permutations, one for combinations. So we have 2 generator functions, one to generate permutations, the other one to generate combinations. And then after this, okay, we are going to move on. Oh, this is the wrong class. This is the right class. Okay, so after counting, we are going to proceed to talk about discrete probability. And when we talk about discrete probability, we are talking about, let's say we're talking about 5 tosses of a coin, okay? So some of the questions that I might ask you is, out of the 5, what are the chances that out of 5 tosses that we end up with 2 heads and 3 tails? Okay, so that's basically what discrete probability is going to answer. And I might even tell you, guess what? The coin is loaded. So the chances of landing on the head is 0.6. The chances of landing on the tail is 0.4. So how do you factor that in when you're computing the chances of 2 heads and 3 tails? Is that okay? I mean, so that's discrete probability. It has to do with something that you guys are all familiar with, Pascal's triangle. Are you guys familiar with Pascal's triangle? So what does polynomial has anything to do with flipping coins? This module will explain that. So if you have time, try to read ahead of me a little bit, try to read ahead of the lecture a little bit, because that will prime your mind to absorb all that information when we get to that. Is that okay? So in real life, why do we care about flipping a coin? Okay, let's just say that you're not a gambling type. So why would we care about the chances of having 1 head and how many tails? 1 zeros, anything that's binary, right? So in real life, what is binary? There are lots of things that are binary. Is this bit transmitted, received correctly? Well, that's binary, because it's either yes, it is received correctly, or no, it is not received correctly. Does that make sense? So instead of head and tail, we have received correctly and not received correctly. But why do we care about that? Well, what if I tell you that by empirical experiments, I know that the chances of receiving a bit correctly is only 80%. That's really bad, okay? Because we have 1 chance out of 5 that the bit is not received correctly. So it's a very noisy environment. So if I want to say, well, but I can transmit the same message like how many times, what are the chances that one of those times you're gonna receive the correct transmission? Well, that might be important, right? Or I can say, for each bit, I'm going to transmit it 20 times. Okay? So out of the 20 receptions of the same bit in a very noisy environment, how do you figure out what is the quote-unquote supposedly value of that bit? that might be important, right? Because let's just say that we have two ships, okay, trying to communicate using laser, and there's a lot of atmospheric activity going on, so the chances of receiving that bit correctly, even with laser, is really low. But you cannot just go like, well, let's just not transmit anything, because it's important to get some information across. So you might say, well, we'll go ahead and transmit each bit 20 times. And then you need to figure out the probability of, if I receive this many ones and this many zeros, what is it supposed to be? Knowing the chances of the errors. So that can be important. And that turns out to be something that we can solve using discrete probability, and it has something to do with binomials. So that's what we can talk about either Wednesday. Most likely it's going to be next Monday. And by the way, we are in week 10 right now. This is the first day of week 10. As I told my other class, I cannot believe it because I wish I had more time. I wish this is just the middle of the semester, but it's not, unfortunately. All right, so we'll see how much we can pack the material from here on to the end of the semester. All right, I'll see all of you on Wednesday.